So anyway, the title is entirely due to Irvin, and I thank him for insisting on keeping the title. Now the problem was, what do I want to really say? And I gave him this title very early on when he sent an invitation. I said, I don't do anything intelligent or not even smart. So he insisted on me coming, and I don't regret it because it's been very nice. And indeed, there are things which I would call smart active matter rather than intelligent, but it's a good step. And okay, so thanks for this. Thanks you both for organizing this. It's been very nice and significantly different from the last two active matter things I went to, which were a little bit routine. So that's nice. Okay, so let's start with a wordy thing, which is basically explaining what I want to do today, or what I was forced to do today, given the title and the audience. And so I feel a bit odd because I don't really I don't work on intelligent or smart active matter myself, but I'm not the only one in the audience, so we are. So I recommend reading from Herbie Levin and Daniel Goldman. They once put a small thing on archive, 4 pages, is it? And I tried to get it published in PRL, but that proved it impossible. Now it's published in Soft Matter, more or less under the same form. It's good reading. It explains to you why, if you really want to be serious about living active matter and biology, an intermediate step from those coming from dumb active matter is something that they define as smart active matter, and they, basically units that integrate regulatory, decision-making, sensing, etc. All the things you can think of with real cells like Andreas talked about. But the things Andreas is doing these days is just too intelligent for me. So anyway, so me, I do none of this, of course, and I still work on dumb active matter, and my problem is that this dumb active matter is doing smart things, maybe too smart for us to really understand, and even many of the simplest models we all know about, in fact, have very deep things that we did not understand. So that's not exactly what I want to show you today. So for me, understanding means understanding emergent collective behavior from the bottom, from the unit level, whatever, microscopic level, whatever you want to call it, all the way in some ideal world to field theory and algae, and of course, we almost never get there. So anyway, I give you some examples today, and I know already that I have at least one too many. I have 3 topics, and now you can have a look at them. Okay, and you have to tell me which one you do not want to hear about. Okay. So this order can be changed. It doesn't matter really. So briefly, the first one is about things Quinker rollers do that cannot absolutely be described at any Vic-Shed total 2, whatever it is, thing, which is usually the theory invoked to describe these things. The second one is possibly, because we cannot prove it yet, topologically protected edge flows in colonies of swarming bacteria at the edge of these colonies. Okay, that should interest Nikta at least. And the third one is cellular active nematics, which are neither extensile nor contractile. That should interest Julia in principle. But anyway, so if nobody says anything, I will proceed and probably have to stop somewhere. Unless somebody wants to hear about Quinker rollers. No? Okay, let's go. Anyway, I proceed and we'll see how goes it. So first of all, this is the experiments in particular, and also the modeling, the little modeling I will show actually later in the end, has been done by these people. So these are all Chinese experiments. I think we should have a word, some thoughts for the Chinese community, which is now publishing more PRL than any other country, including the US, and I don't see many Chinese here or elsewhere. There's this growing disconnect, which is worrisome. Anyway, so just to tell you that some very nice things are being made in China, including by Japanese professors. So Masaki Sano, as you know, was in Tokyo, has been in Shanghai for a long time, and this is the third part, which you will probably not see, is done by him. Okay, so Quinker rollers. I assume many of you know about the Quinker rollers, etc. If you put a colloid particle in a weakly conducting fluid, you apply a constant electric field across the fluid and pass them with strength, EC, the colloid starts rotating on itself. This has been studied by Mr. Quinker at the late 19th century. Okay, if a particle is heavy enough, it will fall at the bottom of a dish and it will roll. And these particles have no intrinsic axis, no chirality, they're reasonably spherical. So they will choose a direction into which to move, which is decided by fluctuations if it's an early particle. Now this has been studied in particular in the context of active matter by Denis Barthelot and company and Olivier early on, in a regime where you are past, of course, this threshold EC, where all particles start moving and they do some things together and they flock. Okay, this is claimed to be actually described one of the best examples of finally some system that behaves like the Vic-Shank model or the Tono 2 equations. And I personally believe it's not true, but anyway, let's not get into this today. There is another thing that is well known in the Quinker world is the threshold EC is the threshold for one particle in some infinite space. Okay? If you put two particles next to each other, the threshold is lower. It depends on the geometry of this. There's a paper by Das and Seeon here which calculates all these things. So there's a range of about 10 to 20%, it depends on particular experiments, below EC, where sufficiently dense packets of particles will go into motion, whereas the isolated particles will stay. And the little movie which you may have seen, I'm not sure, let's repeat it. So here you saw the speed is the color is speed, and so isolated particles like this do not move, but some denser already moving may entrain some others, etc. So in this regime, where again it's not, you don't have to fine-tune so much the field strength, it's about 10 to 20% below EC. You will can observe all kinds of interesting collective phenomena. So these are experimental results. Again, the color is speed, and in particular, I want to speak a bit about these vortices here. Standing in the middle of nowhere, and no walls. You know, if you put fish in a fish bowl, they will go in a vortex. If you put the supercritical Quinker rollers in a disk, they will also form a vortex. Here, there's no walls. There are no walls. And that's what, and I, you know, okay, so it's a movie of it. I was brief. Again, okay. And depending on the experimental conditions, whether you're lucky or not, these vortices can grow apparently to an arbitrary size, although experimentally, of course, you're always limited. If a big packet of moving particles comes in, then it can destroy the vortex, but if only small packets come in, they will aggregate and form a larger and larger vortex. Okay, so this, I don't know any dry active matter model reasonable, meaning without explicit chirality, which these particles do not have, without even alignment, which these particles in fact do not have. Anyway, we can produce these self-standing vortices in the middle of nowhere. So, and we, of course, I'm showing this to you because it's nice and also because we succeeded in modeling this properly. I think, of course, you can do 3D, let's say, faithful, complicated electro, hydro, friction, etc., complicated things, and of course, and you will be next to impossible to see many particles, of course. So what we want is an effective 2D model, which is based on existing mechanisms, and is simple enough to be coarse-grained, which is the thing which we have not done yet. But anyway, so now we are there. We have, let's say that at the end of this, we have a hybrid model. We have particles in a fluid, and the interactions are, so you need, you need a stop and go, you need a stop and go mechanism here, which mimics the fact that if you have neighbors, you will start moving. If you have moving neighbors, moving people passing next to you, they will entrain you. You can stop by yourself. If you're isolated, you will stop, and so on. So these stop-and-go mechanisms are on top of what you would think are the usual interactions here. The modeling, I don't show you any equations. It's a bit boring, but it's basically interacting particles in a Stokes fluid. You have the particles, they have short-range steric repulsion. They have mid-range, at mid-range, what is it? The medium-range repulsion also due to vertical dipoles. When they start moving, these dipoles induced by the field are tilted, so this introduces some extra interaction. And there's polar entrainment of the fluid, because they are on the substrate, they're all on the substrate. And this is the fluid entrained by one particle. The fluid flow created by one neighboring particle will align neighboring particles sufficiently. So all the alignment is in the fluid, in the Stokes fluid. It's a very simple thing. The particles are, what they are, essentially pointwise, except repulsion. So it's a very efficient numerical model, and it works very well. In principle, it's simple enough to be coarse-grained, even though it's harder, and it works to a point of being qualitatively okay, quantitatively, semi-quantitatively okay, and in particular, you can have it's a regime where you have some vortices forming and some donuts or whatever. These donuts are basically in between a stream of particles and a vortex. And this is a fancy, complicated picture of a stupidly large vortex that we generated patiently, particle by particle, in an otherwise infinite space here. So this is a model which has, apart from a degree of incompressibility of the effective 2D fluid, no long-range interactions, and yet produces arbitrarily large vortices, which are very, very stable structures. And this, for me, I was always intrigued by all these vortical structures in fish, etc. And all the models you can think of, they have a long-range thing that makes sense. So here, the key thing is that particles who try to escape, they are entrained by the neighbors, they try to escape, they're alone, so they stop, and then some fluctuation will catch them again. So that's essentially what happens here. And you see, so we don't have any continuous theory for this.
I'd say if there would be some individual vortices, they must coarsen and in the end get to a...
They will, the larger the size, the weaker the diffusion of the whole thing, of course. But in principle, yes. Yeah. And that, but in the actual experiments, it's mostly, you have like this intermittent propagating along semi-fractal clusters of, and some groups of particles, I think, will join a vortex and make it bigger. If a group is too big, it may be too strong a perturbation for the vortex. And so this is a good case also for studying what is called order by chaos. You reach an absorbing state, you can, and that absorbing state, if you're right in the transitional region, should be hyper-uniform, and etc. Not enough control and not enough time in the experiments to actually do this. But it's an interesting, the only difference is that you have a fluid, and so numerically we never studied this, but it's something that could be of interest. Maha?
Is there a nucleation question over here of how large critical...
Well, we know exactly, more or less, I mean, clever people can calculate this on the full 3D problem. What's the threshold depending on the distance for two particles? If you have three, I think it's already too complicated, but we have good indications of what triggers motion. If you have two nearby, or one passing nearby another, it will entrain the other one, because locally the configuration will, plus the entrainment of the fluid, locally the configuration is such that the Quincke threshold suddenly, locally reduces, lowers itself. So we understand this. At the level of two particles, I think more or less everything is calculated. Three, I think, is already too many combinations. So. Yes?
The particles at the boundary, when they join, do they create a shear, or do they just kind of like...
They kind of join. I mean, if you look at the title page of the talk, if I go back there, yes. This is also the same experiment. You see interesting, see one vortex got destroyed, the other one recruited others. I mean, We have many movies of such. You see, you have some kind of semi-percolating, it crystallizes locally. This intermittent space-time dynamics, in principle, is very interesting, but the experiments to get enough statistics for these phase transitions would have to be run for hours, and usually after half an hour, the electrons fry, so you just throw out the cell. So it's not convenient, not to mention that you need many. Okay, so I will try to go to the second part directly, and it will be an achievement. So the second part, if I go at this speed, maybe I can make it, is about these possibly topologically protected flows. So let me go next. I'm moving. So what about chirality in bacterial turbulence? We've seen bacterial turbulence here also. And whereas everybody knows the bacteria themselves, at least regular propelled bacteria, are chiral objects which actually have chiral trajectories in 3D if you look carefully. There's wobbling of the head, etc. Active turbulence as it is observed or described by theory totally neglects. There is no trace of that chirality at the local scale. So, whereas it is well known that in some spectacular cases like this, in special growth conditions, colonies can grow with obvious chirality here. Okay, so Repeng Chang in Shanghai decided to study actually a bug in this family under wet conditions, under fairly standard growth conditions on agar, like the things biologists do when they need bacteria. You know, you put it in the oven for at 30 something degrees in the evening, and the next morning you can work on them, but in between during the night all kinds of things happen. So this is Penis-Bacillus vortex. It is known to form vortices, and the chirality of these vortices is actually it's not clear. It's not always clockwise. It depends on the condition. So anyway, here you will see a long movie, but I will make it briefer. So this is, after some hours of growth, this is centimeters here. If you have a good eye, this projector is pretty good. You see motion inside, swarming, and you can even see that all along the boundary, whatever the local curvature, there is a flow. This is a closer view. If you have a good eye, you see that here we're going clockwise, and around the islands we're going counterclockwise. And they've done hundreds of experiments. A given experiment has hundreds of islands and a very large contorted boundary, and it's always like this. So there is explicit chirality breaking, and I defy you to find the chirality in the bulk. All kinds of clever things we've tried, from the velocity field, etc. There is nematic ordering, which you should be able to see now. We're going zooming and zooming. If you have a good eye, you see that there is significant nematic order. You see that this is about 100 microns width. So it's not a single layer of cells or 2 layers of cells, it's really a collective phenomenon. And here you see, well, usual bacterial turbulence, whatever that is. Now this is the closest thing, and you see here that we estimate that there are 3, 4, 5 layers of cells typically in the bulk. They are not really layers, it's very, very dense. Cannot distinguish single cells experimentally. The only thing they can measure is the velocity field. Anyway, so you have, but something they did is to put some tracer particles which are entrained by the fluid, at least it's believed to be entrained by the fluid, and you can track them along the boundary, and you see they can travel for centimeters or millimeters at least. Some of them do come back in the bulk. You see that here there's a little island not visited, not invaded by the colony for some reason, and this particle looped counterclockwise around it. All right. So there's clearly robust edge flows independent of the curvature. Even angular points are followed, and that's for the hard condensed matter people. This is like a bacterial topological insulator, but I see that Peter is sleeping, so it's okay. I said topological insulator. Quantum pole. Okay. We can measure from the velocity field the various profiles of these things that typically 100, they can vary conditions of growth and various things, not too many control parameters here, but basically, and so the mystery, for me at least, is that in the bulk here, this is a vorticity field, and you can more or less threshold it in a clever way, etc. Whatever you do in the bulk here, there is no measurable symmetry breaking, no chirality symmetry breaking. Okay, whereas here, on scales of about, and you see there's a counterflow in fact, on scales of about hundreds of microns, 100 to 200 microns, you have clear chirality breaking, edge flows, okay? So the origin of this is mysterious, okay? I mean, you can say, okay, bacteria have chiral, but of other bugs, E. coli or Serratia, etc., they do not show this at the edge of a growing colony. They tried in various conditions. Okay, so why? Here, in fact, the bugs have a curved body, so banana-shaped, more or less. It's not straight rods. And if you, in other growth conditions, they can move by themselves easily. You can observe individual ones. And what they do is that they basically follow the curvature of their body. You know, their flagellas are bunched on one side, and they go like this, basically following the curvature of their body to very good accuracy, actually. Plus noise, of course, plus collisions, etc., etc. So you say, haha, there are chiral trajectories. But you take your banana this way, and you flip it, then you flip a chirality. So that doesn't explain anything, of course, in terms of chirality breaking. So how come there's still? And then you can see in these growth conditions, and these are interesting movies too, okay? You see that not all of them move. It's difficult to have the conditions of, proper conditions so that individual cells will move, etc. Here you go actually inside the growing colony here. It gets denser. If you have a very good eye, because I didn't choose to show the movie with coloring of the curvature, you see here there's already significant counterclockwise chirality. If you have a good eye, you see it. It can be measured here as a function of a packing fraction, which means the distance to the edge of a colony, of these fast-growing colonies, which are not dense at all. You see that the bias between counterclockwise and clockwise, as measured from the curvature of the trajectories, or the curvature of the bodies, or whatever it is, signed curvature, of course, grows with the packing fraction. So how come that happens? Still not very clear. It's clear that the bias is there even at zero packing fraction. If you extrapolate, in some cases, at least it's very weak, but it's there. So what can happen? You know, clearly the collisions are of these polar moving objects favor the formation of packets and of polar packets, and polar packets with the guys mostly of the same chirality. So that is a mechanism to increase some initial bias. But where does the initial bias come from? We still don't really know. You could say, sometimes, now they can flip. No, but they never flip. So we looked at hundreds of movies, etc. They never flip in conditions where we can track the particles. Sometimes what happens is something like this, which is a very exceptional bit of a trajectory of one particle, of once. It goes this way. I think it started here, I think. Stopped, reversed, and went back on its track for a while. Reversed again here. So you have two reversal events. And they last a few seconds. There are other bugs which have been showing to show this, and what happens is that the flagella gets shedded to the other side of the body, somehow. And because of a flagellar bond or chirality, you can understand that going from clockwise to counterclockwise, or from counterclockwise to clockwise, these reversals are not symmetric. And even though we have no mechanistic serious explanation of this is one clear source of lowest level possible source of chirality symmetry breaking. And indeed, if we measure the rates of these rare events, which takes a Chinese postdoc working for weeks and months, because that cannot be automatized very seriously. There's a significant bias to go for one type of reversal over the other type of reversal. So there is, even at this super low, no interaction level, there is a weak chirality breaking in terms of these reversals being more easy in one sense than the other. Then we imagine this gets amplified, etc. So now we model this, and I skip all the details. What we do again is particles in a Stokes fluid, effective 2D Stokes fluid, even though it's not really, it's quasi-2D here. Okay, the particles align, they are polar, they have some intrinsic chirality, we have two populations slightly biased, okay, and they align nematically, like they should in such dense conditions. And all this is in the Stokes fluid, so this is, of course, images to show exactly the same thing that they measure in the experiment. So this is basically the velocity field of the particles, coarse grains, etc. And you see, well, we have the edge flows, we have counterclockwise here, clockwise here, whatever, etc. Whatever the geometry. And in the bulk, nice movie. In the bulk, and a typical size here, most of the parameters we can know from the experiments. Here we can have something that corresponds to 100 microns or something like that. Now, if you take a fairly large system like this and look in an image like this of a vorticity field, again, if I take one image, you won't see anything. If you run this thing for, I'm not sure, stupidly long times, I think I hit that slide, maybe I can show it, because it goes well now. Okay, I have to go out, sorry. I'll be back in a second. Okay, let me unhide this slide. All right. Here. So that, in that sort of a slab geometry, forgetting about really the center of it, average of a very, very, very long time. The histogram of vorticity looks like this, numerical histogram of vorticity. And you see the red one is the flipped version of a blue. And you see there's a tiny, significant but tiny chirality breaking. So in the bulk, there's still a remnant of actually much larger chirality bias we put in. It gets washed out in the bulk and concentrated at the boundaries in what looks like a very topologically protected. So that's where we are on this problem. What we're working on now, because these models again are simple enough, we check like things, in a fluid, we can coarse grain them properly, and the hope is to, from the continuous theory we get, be able to prove convincingly topological protection, but we're not there yet. How much time, Mr. Chair? 9 minutes?
No time.
0 minutes. Okay, good. I said this. I will not say, I will show something about this, but 1 minute, okay? There are very nice cells to do active nematics with cells, which are neural progenitor cells that Professor Sano and Kawaguchi and others have started working on in Japan and in China. So these cells do this. When they are in a confluent layer, any given cell will do this. They're very elongated, and they do this. It's like a perfect case for an active nematics. And indeed, they form active nematics. There are plus and minus 1 defects, etc. And there's accumulation of cells near the plus 1 defects, in this case, which serve some biological purpose. That's a very smart thing to do, probably. There's a simple linear theory argument if this nematic is extensile, even though the cells themselves look contractile from the point of view of traction force things, which can be discussed. So I don't get into this. So you can propose such a very simple looking linear theory, which was done by Kawaguchi and Sano, and so the effective velocity of the cells is basically given by the active stress, or you have some kind of effective force, active force, if you want to put it this way, some kind of overdamped description. The problem is, if this theory predicts that if you have a +1 defect, which never happens spontaneously for obvious reasons, I mean for usual reasons, that theory predicts that an aster configuration like this will accumulate cells at the center, but a target configuration like this will be depleting cells at the center. Okay? Now, these defects do not appear spontaneously, but you can induce them by small ridges on the substrate. And if you do this, then in the target pattern here, which you show here, there is accumulation. So the cells, they move along the ridges of the target, more or less, but they drift inward. So the effective V field that I talked to you, I'll show you in this simple equation, is actually directed towards the center in blatant contrast with the predictions of this linear theory. And that is contractile behavior, whereas what was seen before is extensile behavior. This is the same cell, the same configurations. And actually they did this, but also coexisting with target patterns, coexisting with spirals, etc. So it's clear that the simple theory I mentioned before doesn't work. And so what we did is from the bottom up, from the dry active matrix of particle doing this, aligning nematically, etc., etc. So deriving hydrodynamic equations, and so on and so on. At the end, we arrive at, to describe the stationary pattern of near a +1 defect, we have arrived to something like this. You know how it's called W now, the velocity field. There's an anisotropic friction, but here you have, and also a pressure term because it's a compressible system now, but the active force, so to speak, corresponding to what you had before is the same term. You have minus zeta Q, minus zeta, what is it? Grad Q, sorry, diff Q. But you have two new terms here. Because Q is large in these patterns, these are equally important as the active stress, so to speak. These terms cannot be classified extensile, contractile, etc. And you can build some kind of picture of the usual active stress term here and the difference between the gamma 1 and gamma 2 things. The experiments are here, and we can measure these two coefficients in the experimental data. So here you have everything is fine and contractile. Here everything is fine and extensile, but here and here this classification does not apply. All right. So this is part of the smart things that we still cannot really understand, but non-active matter is doing. I mean, these cells are not actually very clever. But okay, thank you.